this a private session on power steering, or can anybody get into the act?
Oh, hello, Tech. We're just talking about what happens in the power steering hydraulic system when you turn the wheel. Old Fred here says he's a little rusty on how the control and power systems work.
Sounds like the kind of shop talk that would interest a lot of technicians. Why don't the two of you give the whole subject a going over? I'll referee the contest.
Okay, Tech. I'll start in on the fundamentals, and Jack can take over if I get stuck. The basic mechanical parts of a power steering gear work about the same as a manual steering unit. However, in a power steering gear, what might be considered the ball nut is also the power piston. In strictly mechanical operation, the piston is moved up or down by turning the worm shaft. Sector gear teeth mesh with a rack on the piston to change piston movement to cross shaft rotation, just like a manual gear. As the cross shaft is turned right or left, its pitman arm moves the steering linkage and turns the front wheels.
All right, Fred. That takes care of mechanical action. Now, can you explain how the power assist ties in?
Sure thing, Tech. In a power steering gear, the steering gear housing is also the cylinder for the power piston. With this arrangement, the power piston divides the cylinder into two separate power or pressure chambers, which are connected to hydraulic pressure by individual ports. Now, let's see how hydraulic pressure to these chambers is supplied and controlled. A belt-driven oil pump provides the hydraulic flow and pressure needed to operate the power steering system. Flow to the power chamber ports is controlled by a reaction-operated steering control valve mounted on the gear housing. A sliding spool in the steering control valve has lands which open or close the power chamber ports to determine which chamber receives assist pressure or whether there is any steering assist at all. There's no power assist as long as the spool valve is centered, because both power chamber ports are open an equal amount. This allows hydraulic fluid to circulate through the valve and keeps the pressure equal in both chambers. When the spool valve moves upward, the upper land uncovers more of its port opening to the input flow. At the same time, the lower land blocks input flow and opens its port to the return side of the oil pump. In other words, circulation through the steering valve is stopped and pressure is increased in the upper chamber. At the same time, pressure in the lower chamber is reduced because it is now connected to the pump return line. So, there's a difference in pressure between the two power chambers. This pressure difference moves the piston downward as more fluid enters the upper chamber. As the piston moves downward, it forces fluid out of the lower chamber and into the return side of the system.
Power assist continues as long as the driver exerts turning force on the steering wheel. For a turn in the opposite direction, the same hydraulic action takes place, but valve and piston movements are now in the opposite direction. Now suppose you explain what happens after a turn is completed, Fred.
Coming out of a turn, the spool valve recenters automatically and power assist stops. With the spool valve centered, piston movement can now push the fluid out of the power chamber. This allows the power piston to move back to center freely, so the front wheels can return normally to the straight-ahead position.
Tell me, Fred, do you think you can explain what happens in a power steering gear when the front wheels hit a bump or chuck hole?
I'd sure like to give it a try, Tech. When the car's front wheels hit ruts, bumps, or chuck holes, the steering forces reverse because the front wheels try to take over from the steering wheel. In a car with manual steering, this reverse action can jolt even a firmly held steering wheel. However, with power steering, when a bump, rut, or other road shock tries to deflect either front wheel, the steering linkage transmits this shock force to the steering spool valve through the sector gear and power piston assembly. Because road shock reverses the normal steering forces, the spool valve moves in the opposite direction and causes the power assist action to oppose the front wheel deflecting force.
And that opposing action is one of the reasons why power steering is an important safety feature. Now, Jack, Why don't you explain the fine points of steering control valve operation?
Glad to, Tech, as soon as I clear up a point about right and left-hand worm shafts. The worm shaft in a steering gear with a leading type pitman arm has a right-hand thread for the recirculating balls, while the gear with a trailing type arm has a left-hand worm shaft thread. Both types operate essentially the same, except that movement of the parts is reversed. Now, to explain how the steering control valve is operated, let's use a left-hand worm shaft gear as an example and see what happens when we turn the steering wheel. In a right turn, the worm shaft tries to screw upward out of the power piston. However, since up or down movement of the worm shaft is limited, the screwing action produces a downward force on the power piston. Now, because the front wheels resist turning force from the steering gear, the cross-shaft sector gear opposes the downward force applied to the piston by the worm shaft. But the worm shaft and thrust bearing assembly can move up or down a short distance because there is a small amount of clearance between the cylinder head and gear housing head. This clearance lets the worm shaft react to steering resistance by moving the thrust bearing upward. Thrust bearing movement also acts on the pivot lever, which connects the thrust bearing center race to the steering valve spool. So when the steering wheel is turned to the right, the spool is moved downward to produce right turn assist action. When the turning force on the steering wheel is relaxed, the thrust bearing race is recentered by a combination of spring washers and hydraulically operated reaction rings above and below the bearing assembly. The balance clamping action of the springs provides the basic centering force for the bearing race. In addition, the reaction rings also produce hydraulic centering force when they are pressed against both sides of the thrust bearing by equal hydraulic pressure from the two power chambers. These reaction rings do a couple of very important things. They are designed to equalize the power assist provided on turns to the left and the right. They also regulate the total steering wheel turning force, so the driver will have some steering feel proportional to steering resistance.
Can you explain how the reaction rings work and why the upper reaction ring has more area than the opposing reaction ring below the thrust bearing?
Well, I can give it a good try, Tech. First of all, each reaction ring groove is connected separately to one of the power chambers so that the hydraulic pressure acting on each reaction ring is the same as its chamber pressure. In the straight-ahead position, hydraulic pressure will be the same in both power chambers and in both reaction ring grooves. Now, during a turn, there is high pressure in one chamber and low pressure in the other chamber. The pressure difference between the power chambers produces a corresponding difference in the pressure pushing the two reaction rings against the thrust bearing race. However, in a right turn, hydraulic pressure also pushes the worm shaft upward. This reaction produces more thrust bearing displacement force in a right turn than occurs in a left turn. Now, let's see how the reaction rings balance the power assist on left and right turns. To compensate for the greater thrust-bearing displacement force on right turns, the upper reaction ring assembly has more surface area than the lower ring. When chamber pressure is applied to the upper ring, it produces additional resistance to thrust-bearing movement. This equalizes spool valve movement on left and right turns. Also, the reaction springs and the reaction ring assemblies are designed to slightly reduce the worm shaft thrust bearing's full displacement force and movement so that the driver will retain a steering feel. In other words, reducing thrust-bearing movement causes the spool valve to open the power chamber port slightly less than the amount needed for full boosting action and leaves about 20% of the total steering force for the driver.
That built-in feel is a good feature of our power steering gears. And here's another. The amount of power assist is proportional to steering wheel turning force. In other words, a heavy turn on the wheel gives more power assist. A light turn gives less power assist. And here's where someone can give us an assist and turn the record. Okay, fellas, you've covered operation of the power steering gear pretty well. Now, who's going to tell us about power steering pumps? How about you, Fred?
Pumps are right down my alley, Tech. As you know, our power steering systems may have a pump with a 1.2, a .96 or a .94 cubic inch displacement, depending on the car model. Each pump is designed to meet the flow and pressure needs of a specific application, so pumps are not interchangeable. In most installations, the differences in pump mounting dimensions help to prevent incorrect substitutions. However, you can easily identify each pump. The reservoir diameter is 5 1/8 inches on the 1.2 pump and 4 5/8 inches on the .96 pump. Pulleys for these two pumps are pressed on. The .94 pump is entirely different. The pump shaft is threaded for a pulley retaining nut. This pump also has a long oval-shaped filler tube instead of the round tube used with the other two models. These pumps all operate on the same basic principle. The two larger pumps are the slipper type. The .94 is a vane type pump. Each pump has a flow control valve to regulate flow in the system at all engine speeds, plus a pressure relief valve.
Why don't you explain why we need two valves, Fred?
Okay, Tech? Pump output normally increases as engine speed goes up. And if it weren't for the flow control valve, the flow rate would become excessive at higher speeds. This would waste engine power and overheat the hydraulic fluid in the system. Now, the flow control valve design varies in each of our pump models. However, since they all accomplish the same thing, we can use a .96 pump as an example to describe flow valve operation. This flow control valve has a valve orifice and a stepped metering pin. Output flow moves the valve. The metering pin is stationary. Here's how it works. From engine idle to 3,000 RPM, the metering pin's small diameter is in the valve orifice. This permits full output flow in the system to provide ample power assist at lower engine speeds. Above 3,200 RPM, the valve moves inward so that the metering pin's large diameter is in the valve orifice. This produces maximum restriction, but does not block flow through the valve. At the same time, the valve also opens the input side of the rotor chamber slightly, so part of the fluid bypasses the flow valve and circulates back into the chamber. The restriction and bypass work together to prevent excessive flow at higher speeds.
The metering pin is preset at the factory to provide the correct flow rate at all system temperatures and engine speeds. It must not be altered or readjusted for any reason. Now, how about giving us the story on the relief valve?
I was just coming to that, Tech. Let's suppose the front wheels are turned as far as they'll go. Piston movement is stopped, and pump pressure increases behind the piston. Pressure in the system increases until it reaches the opening pressure of the pump relief valve. At this point, the valve opens and bypasses the fluid to the pump reservoir.
And that should take care of pump operation. Now, do either of you have any servicing or troubleshooting pointers you'd like to give out? How about you, Jack?
Well, I usually check the quickies first, like the fluid level and drive belt tension. Often a little fluid or a belt adjustment is all that's needed. Pump noise is another trouble that's easy to check out. Just pour a little water on the drive belt. If the water eliminates the noise or changes the sound, you've got belt or pulley noise. If the noise doesn't change, loosen the pump drive belt and run the engine at normal speed. If the noise still continues, you'll have to look for something else, like the water pump or alternator.
Good points to remember. But where do you go from there if there's no steering assist?
Lack of assist may be caused by a stuck flow control valve in the pump. Here's a quick way to check that possibility. Speed up the engine a couple of times to build up pressure and load the flow control valve. If this pressure treatment restores steering assist, you'll know the flow valve was stuck. And speaking of valves, the pump flow control valve, as well as the back pressure and spool valves in the steering gear, are closely fitted and must be handled with care. Here's an important point to remember. The sharp valve land edges must not be rounded off when a valve spool is cleaned or when burrs are removed. However, deep scratches or nicks must be carefully smoothed out, or the valve may stick.
Do you know why sharp valve land edges are so important?
Sure, Tech. Sharp land edges wipe the valve bore and minimize valve sticking. Besides, those sharp valve land edges ensure precise flow control.
Treat these valves like fine jewelry. You'll find some mighty important tips on cleaning and polishing valve spools and bores in the reference book. So be sure and bone up on that information. Right now, let's get back to troubleshooting. Can you explain what the pressure test tells you, Jack?
Sure thing, Tech. For instance, correct pressure at low engine speed tells me there are no obstructions in the hydraulic system and pump flow is probably okay. However, if I get correct pressure at higher engine speeds, but no steering assist, it usually means that the pump's okay and the trouble's most likely in the steering gear. When there's less than the normal amount of steering assist, you may have a faulty pump relief valve or a sticky pump flow valve. To tell which valve is causing the trouble, I install a new pressure relief valve and repeat the test. If the pressure now checks out, I'm in business and the valve stays in. Where there's no change, it can be the flow control valve or the pump itself may need reconditioning. One more thing. Where you find dirt or chips in a pump or reservoir, you can be sure that the whole power steering system has been affected by the foreign material. You'll have to completely recondition both the pump and steering gear in these cases.
And let me warn you, don't make the mistake of installing a new pump as a cure-all for power steering problems. Far too many good pumps are replaced without reason. Just remember that a customer won't enjoy paying for a new pump if the trouble's in the steering gear. Now, how about you, Fred? Any servicing kinks you'd like to add?
Just a few things in general, Tech. Like making sure there's no foreign material between the front insert and the cam insert, or in the housing when putting a pump back together. Even a tiny speck of trapped dirt here will cause excessive rotor end clearance, which will reduce pump efficiency. Proper installation and seating of the pump rotor slipper springs is also very important. These springs must stay upright in the rotor slot pockets when you install the assembly. If a spring slips sideways, it'll jam the slipper against the cam insert and cause pump failure.
Don't forget steering shaft and coupling alignment.
Yeah, glad you reminded me. If the shaft end isn't centered in the coupling, it can butt against the worm shaft and affect steering control. Any bind in the steering shaft or coupling can cause wonder, unequal assist, or returnability problems. Now, to finish up, always be sure to use the correct pressure and return hoses for replacement, or you may have noise problems. These hoses are designed to control hydraulic pressure noises, as well as flow and pressure in specific steering systems, so don't try to use substitutes.
Be especially careful to use the correct part number replacement hoses on models which previously had a steering system oil cooler. These hoses are a special high temperature type that must not be replaced with regular power steering hoses. And that brings our power steering session to a close. There's more in the reference book about power steering hoses and other service pointers, as well as some extras on the things we covered in this film. The explanation of power steering gear and pump operation should help you to better understand what power steering trouble symptoms mean and how to locate the trouble source more easily. So whether you're overhauling a power steering gear or only making a simple adjustment, be sure to follow your service manual instructions. Do each job carefully and always keep it clean. See you next month.